Hi, this is Bono. Today I'll explain Kirchhoff's laws. With Ohm's law alone, there are situations where it's hard to solve a circuit that has two sources, or one where the current splits across several paths. The powerful tool for exactly those cases is Kirchhoff's laws. By combining two laws, you will be able to set up equations for the current and voltage in any circuit, no matter how complex. They are the absolute basics you can't do without as you learn circuit analysis, so please watch through to the end. First, let me explain the first law, KCL. KCL stands for Kirchhoff's current law, taking the initials K, C, L. What KCL says is simple. The point where wires branch in a circuit is called a node, and the total current flowing into that node equals the total current flowing out of it. The reason is that current is the flow of charge, and the charge is neither created nor destroyed at a node. Picture a junction in water pipes. The amount of water coming in always equals the amount going out, right? Water never disappears inside the junction. Current is exactly the same. It is never lost at a node. It's easy to feel that current gets weaker after branching, but that's a misconception. Correctly, after branching the current only splits and the total stays the same. Next, let's look at the procedure for writing an equation with KCL. The procedure is simple. Pick one node and write out every current involved at it. As in the first equation, if you take currents flowing into the node as positive and currents flowing out as negative, the algebraic sum of all the currents is 0. For example, if I1 flows into the node and I2 and I3 flow out, then as in the second one, you get the equation I1 minus I2 minus I3 equals 0. There's an important point here. You may assume the current direction yourself at the start. Even if you don't know the real direction, just assume one and set up the equation, and the result will tell you. If the result is positive, it matches the assumed direction. If negative, the real direction is simply opposite. Getting the correct answer even with the direction wrong is one of the strengths of KCL. Next is the second law, KVL. KVL stands for Kirchhoff's voltage law, taking the initials K, V, L. What KVL says is also simple. Going once around any closed loop in a circuit, that is, a path you can travel in a full circle, the algebraic sum of the voltages is 0. The reason it's 0 is that voltage is the potential difference between 2 points, and if you return to the same points, the potential difference returns to 0 too. Picture a mountain trail. When you walk the trail from the start and come back to the start, the total change in height is 0, right? Whatever path you take, you return to the same height as the start. Voltage is exactly the same. Going once around a closed loop, the rises and the drops always balance out. By the way, the E in the equation is the EMF, the force with which the battery pushes the voltage up. V is the voltage drop, the potential difference across the resistor. Now let's look at the procedure for writing an equation with KVL. First, choose one loop to work with and decide a direction to go around it. Clockwise or counterclockwise, either is fine. As long as you go around consistently in the same direction, you'll get a correct equation. As in the first one, taking the spots where the potential rises as positive and where it drops as negative, and adding up all the voltages, the sum is 0. For example, in a simple loop where the battery R1 and R2 are in series as in the second one, with the battery EMF as E and the voltage drops of R1 and R2 as V1 and V2, you get the equation E minus V1 minus V2 equals 0. This equation also means that the resistors use up all of the energy the battery supplies. Note that whichever loop direction you choose, all the signs just flip, and you end up with the same answer. Here, let me organize an important idea common to both KCL and KVL. It's that you may freely assume the directions of currents and voltages yourself at the start. If you do the calculation and the result is positive, the assumed direction was correct. If negative, the real direction was simply opposite to the assumption. This is very important because it removes the worry that you can't set up an equation unless you know the directions. Even if the assumption is wrong, the math leads you to the correct answer. Until you get used to it, fixing a rule such as assuming all currents point right or down helps avoid confusion. Now let's combine KCL and KVL and actually solve a circuit. Here we'll use a circuit combining the sources E1 and E2 and the resistors R1, R2, and R3. First, as the first equation, apply KCL at a node of the circuit. If I1 flows into node A and I2 and I3 flow out, then I1 minus I2 minus I3 equals 0. Next, as the second equation, apply KVL to the left loop, loop A. Loop A runs through the source E1, the resistor R1, and the resistor R3, so going around clockwise, E1 minus R1 times I1 minus R3 times I3 equals 0. Then, as the third equation, apply KVL to the right loop, loop B. Loop B runs through the resistor R2, the resistor R3, and the source E2, so going around clockwise, R2 times I2 minus R3 times I3 minus E2 equals 0. Solving these three equations as a system gives you all the currents, I1, I2, and I3. The basic flow is to apply KCL once at a node and KVL once at each loop. After that, you just solve the simultaneous equations you learned in middle school math. Now let's plug concrete numbers into the three equations we set up on the previous slide and solve them. Here we take E1 as 8 volts, E2 as 4 volts, R1 as 2 ohms, R2 as 3 ohms, and R3 as 2 ohms. Substituting these into the first KCL equation, we get I1 minus I2 minus I3 equals 0. Substituting into the second equation for loop A, 8 minus 2 times I1 minus 2 times I3 equals 0, and rearranging I1 plus I3 equals 4. Substituting into the third equation for loop B, 3 times I2 minus 2 times I3 minus 4 equals 0. Sorting these three together, we find I1 is 3 amperes, I2 is 2 amperes, and I3 is 1 ampere. Since the answers are all positive, we can also confirm that the current directions we assumed at the start were all correct. Here's a piece of field know-how. The KCL/KVL equations you set up by hand are actually computed by the circuit simulator SPICE in exactly the same way. SPICE is used in software like LT-SPICE and Multisim, and it's a tool professional engineers use daily for design verification. Inside the SPICE, KCL is applied at every node and KVL around every loop to build a large system of equations which the computer solves in an instant. In other words, what you learned by hand today is exactly the same procedure the computer does automatically. Being able to set up the equations by hand is very valuable because it lets you sanity check whether the simulator's output is correct. Now let's organize what we learned today with a quick quiz. I've prepared 3 questions. Pause and give them a try. Question 1. The total current flowing into a node equals the total current flowing out. True or false? Question 2. When applying KVL, the direction around the loop must be fixed to clockwise. True or false? Question 3. When I1 and I2 flow into node A and I3 flows out, which is the KCL equation? Option 1, I1 plus I2 equals I3. Option 2, I1 equals I2 plus I3. Option 3, I1 plus I2 plus I3 equals 0. Here are the answers. Question 1 is true. Because current is conserved at a node, the total flowing in and the total flowing out are always equal. Question 2 is false. KVL holds whichever direction you choose to go around the loop. There's no need to fix it to clockwise. Question 3 is option 1, I1 plus I2 equals I3. It's the KCL statement that the sum of the inflowing I1 and I2 equals the outflowing I3. If you answered option 3, take another look at how the signs are set. Taking I3 as outflow and therefore negative gives I1 plus I2 minus I3 equals 0, which is also a correct statement. So today, I've explained Kirchhoff's laws. Looking back on today's flow as one thread, it goes like this. Charge is not lost at the node, so KCL holds, and you can set up the equation that the total current in equals the total current out. Potential returns to its original value after one trip, so KVL holds, and you can set up the equation that the algebraic sum of voltages around the loop is 0. By combining these two conservation laws, you can set up and solve simultaneous equations even for complex circuits with multiple sources and resistors. Also keep in mind that you may assume current and voltage directions freely, and a negative result tells you the reverse direction. That's all for today. Thanks for watching.